No, it's,
Yeah,
it's good. All right.
Yeah, I think that's what
So, the homework go okay for you guys? Any problems or issues with the homework or anything like that? Questions? Something like that? Okay. Some of you guys have joined the Facebook group, so that's great. Some of you guys still have not, so I just want to encourage you guys to do that. It's not mandatory, it's not required, but I do think it's a great thing available. And some of you have not given me your email address
I did that today. I didn't.
through that Google Doc. So it's on homework 1. There should have been something that said task to do this. Follow this link, and you enter your email address into the Google Doc. Please do that. Periodically, I do send out email announcements, and if I don't have your email address, you won't get my emails. So anyway, any questions on anything from last week or anything like that? Yes.
I think it was the last question, the entire homework, which was about rescue, Wayne
Okay.
rescue, and it was asking to find the center. The way you solved the problem was sort of like there wasn't a formula. You just deduced that okay, this is the center. So I was curious how you arrived at that, rather than like looking at the bar graph.
Right, just looking at the bar graph without actually adding up numbers or anything like that. So I might have just mentioned this in passing last week, but I will go over it in a little bit more detail. When we're talking about the center, and in particular, when we're talking about the mean can also be thought of as the balancing point of all the numbers. Okay. So this is the center, one of the measures of center, but it also can be thought of as the balancing point. Of the numbers. So if you have a histogram that looks something like this, okay, just imagine that we are trying to put this shape somewhere on a seesaw, and we want to know where to put that fulcrum, that little triangle, so that the object stays balanced. Okay, and if I put the triangle here, maybe it'll tip over this way, or I mean, if I put the triangle here, this thing will probably will tip over. So, but if I put it over here, it'll also tip over. So we are looking for where we can place that balancing point, and I would guess it's going to be somewhere, yeah, probably somewhere around here, and this will probably stay balanced. You've got because of these small pieces out here, which have a little bit more leverage, the tipping point is somewhere around there. Okay, and this can be thought of as the mean. Okay? Now, of course, the mean is also the exact same thing that we learned when we learned about averages. So when you hear the word average, a lot of times they're talking about adding up all the numbers and then divide by the number of numbers. Okay. And the formula that you might see for this, okay, if I can write out the formula, is using this symbol here. This looks like a sideways M or an E almost, but it's actually the capital letter sigma which means sum or add up all of your different numbers, each different y, and then divide by n the number of numbers you have. So this just means this is saying the exact same thing as this. This part, this symbol means add up all the y's, and this says divide by n. And this is this just means symbol to mean add up all the numbers. Okay, and that's the mean. And so when you see a picture of a histogram or a distribution or a set of numbers, sometimes you can eyeball the center or the mean just by kind of thinking, you know, if I had to balance this, where would I balance it? Yeah.
I used to be confused for chapter 3, number 28, well, it's revisited the last part. Do the variables qualities and sex appear to be independent?
Okay.
I'm just confused as to what qualifies variables being independent from each other.
Okay, so independent, and we haven't really gotten really into this, but the idea of independence, so okay, the idea of independence is that what happens in one variable does not have an effect on the other variable. Okay, so if we say two variables are independent, that means what happens to one variable does not influence what happens to the other variable. Okay, if they are not independent, they're dependent, then if altering one would have an effect on the other variable. So two variables So in the example or the exercise where we are looking at political opinions and gender or sex, we see that the distribution of opinions for the men is different from the distribution of opinions for the women, which means that one variable does have an effect on the other variable, and it doesn't give us any explanation why, but just from looking at the data, that is what we are observing. We're seeing that the distribution of opinions for men is different from the distribution of opinions for women. Okay, and so in that case, they would not be independent. All right, good. Anything else? Yeah.
Last week you didn't cover a couple topics like standard deviation or outliers.
Right.
Are you going to go over that tonight, or?
Yeah, we're going to do that right now.
Okay.
So, okay. All right. So let me. So continuing on, tonight we're going to finish up chapter 4, and then we'll go through chapter 5 and chapter 6. So just a recap of last week. We started off with just, what is data all about, okay? And we talked about, we mentioned categorical and quantitative variables. Talked about the who, the what, etc. Once we talked about that, we moved on to chapter 3, which was all about categorical variables. And we learned how to create frequency tables, bar charts. After we created frequency tables, we also created contingency tables. And we learned about, do we call them conditional distributions, or?
No.
What did we say?
The book says that.
What is that?
We call it distribution.
We just call them distributions.
Right.
Yeah, conditional distributions. Okay, contingency tables and conditional distributions. Okay. And these were the tables where we had two categories at the same time, or two variables at the same time. So this was like the Titanic data, etc. And all of this was categorical variables. Okay. And then we moved on to quantitative variables. And we want to learn how to describe distributions of quantitative variables. Okay. And one of the basic tools we learned was a histogram. We also learned the stem and leaf plot. Very closely related to the histogram. And when we talked about describing distributions, I gave you this acronym of CUS, and we talked about a few of them, but not everything. Okay, and so we will today we'll finish up the remaining items in CUS. So the C represents the center, and we did learn the mean and the median. Okay, now if as I'm going through this recap, if you feel like I didn't do a good job explaining or describing any of these topics that I'm mentioning, please pause me and have me go over them. Okay. So U, I said this represents unusual. Okay, and I know I did not really cover this last week, so to be covered today. We have the S for the shape. Okay, and regarding shape, we can talk about skewness or symmetry. Right skewed, left skewed, or symmetric. And then we have descriptions about how many peaks we have. Unimodal, bimodal, etc. And the final S that we have to talk about is spread. Okay. And regarding spread, we have things like the range, the interquartile range, and today I have to talk about the standard deviation. Are we feeling okay about the interquartile range? Yeah. Okay, finding quartiles and then finding the things in, or just the distance between the quartiles. Okay. Because we will see the IQR coming back again later today. So let's talk about the spread and the standard deviation. Alright, so the standard deviation is a way for us to describe the spread. Okay, all it is, this is just something that describes the spread. Okay, this is the mean is a number that we use to describe where the center of the numbers lie, the center of the distribution. The median is also a different number that we use to describe the center. In this case, the standard deviation is a number that describes the spread. Okay. Describes the spread. So a smaller number, a smaller standard deviation means we have less spread. A larger standard deviation means we have more spread. Okay? Okay, and I will abbreviate standard deviation as SD. Okay? Means little spread. Okay, and then on the other side, larger SD means more spread. Okay, so if I drew a histogram, looks like this versus one that looks like versus one that looks like this. Okay, which one has the smallest standard deviation? This one. Okay, so this would have the smallest SD. Which one would have the largest? The middle. Okay. And then this is something in between. Okay. Alright, so the idea of spread is, are all of our numbers clumped together or close to the center, or are they more spread out? Okay. So so here's this is something that's going to be a little bit trickier. So let's take a look at this. So this is a histogram where there's only 3 different values. Okay. And then here's another histogram. Again, we'll say 3 different values or 3 different things. Okay. So between these 2 histograms, which one has the larger spread? One left. So, all right. So who thinks this one has more spread than this one? Okay. Who thinks they have the same amount of spread? And who thinks this one has more spread? Okay. So, if we were talking about the range, okay, the range is just the difference between the smallest point and the largest point. These 2 things would have the same range. Okay, these 2, because the distance from the smallest point to the largest point, in this case, is also the same as the smallest to the largest here. But here, when we're talking about spread, the idea is, are the numbers clumped together or are they spread out? Okay, another way we could think about this is, are more of the numbers closer to the middle, or are more of the numbers far away from the middle? Okay. So if more of the numbers are closer to the middle or closer to the center than they are far away from the center, the one where they have more numbers closer to the center has less spread. Okay, the numbers aren't spread out because they're more close to the center, and the numbers where, or the distribution where the numbers are far away from the center, has more spread. Okay, they are more spread out. They are not as clumped together. And the idea of clumped together comes from the idea idea of talking about the center here. So between these two, which would you say has more numbers closer to the center? The one on the left. Okay, so this one has more numbers closer to the center. This one, most of the numbers are far away from the center. So in this case, this would have the smaller standard deviation. And this would have the larger standard deviation. Alright, so when you see numbers and we're talking about spread and standard deviation, this is what I want you to think about, okay? Where are the numbers closer to the center? Are they farther away from the center, okay? We'll get into the formulas and actually finding out the actual values of the standard deviation, but this is the big picture, this is the important part of what the standard deviation is about, okay? So, let me just write. Okay. Are more numbers closer to the center? Right. This means small standard deviation, or are more numbers far away from the center? This means larger standard deviation. Oh, you can't read that. Okay, well I will, alright, so I'll let you guys copy that while I start to erase. Alright, so I hope that's okay. Well, what can you do? Alright, so that's the idea behind the standard deviation and when we're talking about spread. Okay? I'm going to write down well, let me talk about the steps to calculate the standard deviation. Okay? And then I will give you a formula which covers all of the same steps. And it might look like a scary formula, but it's not. Okay? So let's say we are looking at some numbers here. Okay, so let's say we are looking at a plant, okay, and we want to see how much this plant grows in a week, okay, and we let's say just because we don't want to base all of our answers based on one plant, we're going to look at 5 different plants, and we want to see about how tall this plant grows after a week. Okay, so these are let's say these are the measurements we come up with. Okay, so after 1 week, one of the plants grew let's say 4 centimeters. Right, and all of my measurements will be in centimeters here. So let's say one plant grew 4 centimeters, another plant grew 6 centimeters, another one grew 3, something else grew 7 centimeters, and let's say one of them grew 10 centimeters. So we have 4, 6, 3, 7, and 10. Alright, so the first step, step 1, sorry, I'm going, I didn't plan my board space correctly. I'm going to just rewrite these same numbers here. I've got 4, 6, 3, 7, and 10. so the very first step is to find the mean, okay? Calculate the mean. Alright, so in this case, what is my mean? I have to do the sum of all of my different values, divide by how many I have. So I do 4 plus 6 plus 3 plus 7 plus 10 divided by 5 numbers. I get 30 divided by 5. My mean is equal to 6. Okay. The second step is subtract the mean from each of the numbers. So if my mean is 6, I'm going to subtract 6 from each of these numbers. And so here I get 4 minus 6 is negative 2, 6 minus 6 is 0, 3 minus 6 is negative 3, 7 minus 6 is 1, and 10 minus 6 is 4. Everyone's good so far? Okay, so the difference, or the distance from each point from the deviation is this number, okay? And this is, the distance from each number to the mean is known as the deviation. So that's basically, this negative 2 tells me 4 is 2 points below 6. This says 6 is 0 units away from 6. 3 is 3 units below 6. 7 is 1 unit above 6, and 10 is 4 units above 6. Okay, that's what each of these things are. And this is known as the deviations. Okay. Subtract the mean from each number. This gives us our deviations. Deviations from the mean. So, if we were talking about the quote standard deviation, okay, what you might think what we should do is just average the deviations, okay, and we could add these up and divide by how many numbers we have. But there's an interesting thing is that when you add up your deviations, you always end up getting 0. Okay, so one thing we're going to do instead is that we're going to square everything, and that makes the positives and negatives go away. And then we're going to find the average of the squares, okay? So the next step is going to be square the deviations. So negative 2 squared gives me positive 4. 0 squared gives me 0. Negative 3 squared gives me 9. 1 squared gives me 1, and 4 squared gives me 16. Is this okay with everyone? Square the deviations. And now we are going to find, quote, the average of the squared deviations, okay? So this would be add up the squares and divide by how many numbers you have. Okay, this is basically finding the average of our squares. So in this case, if I say that the sum is going to be 4 plus 0 plus 9 plus 1 plus 16. This adds up to 30. Oh, I'm sorry. It's not divide by how many numbers you have. Okay, let me okay, this is sorry. Step 5 is actually divide by n minus 1. Okay, divide by n minus 1. Okay, so if we were finding the average, we would divide by how many numbers we have, which is 5. But in this case, we're going to divide by n minus 1. Okay, so is this part okay? Adding up the squares, 4 plus 9 plus 1 plus 16, that adds up to 30. All right, and then the next step is we divide by n minus 1. So in this case, 5 minus 1 is 4, so I get 30 divided by 4 is equal to 7.5. Okay, so you might ask, why are we dividing by n minus 1? There is an answer, but it is beyond the scope of this course. If we look at the calculus background behind all of this, there's something called Bessel's correction. If you're really interested, you can look this up on Wikipedia yourself, okay? Bessel's correction. But there might be 2 L's, I don't know, something around there, okay? But just suffice that we're going to say n minus 1 divided by n minus 1, yes?
Don't we use, is there, or maybe I'm getting confused, but is n plus 1 used in another formula?
Plus 1? The n plus 1 over 2th position, in finding the median to find the position of the number, okay? Alright, so we're just going to divide by n minus 1. I'm not explaining why, but just remember it's n minus 1. And then the last step is take the square root.
It's called Bessel's
Correction. Bessel's correction. Okay. If you haven't taken calculus, you probably won't understand anything that's on that page. Okay. So, but if you have, and if you're interested, it's interesting. Okay. It's talking about the population and things like that. But Bessel's correction, it's there. Okay. So 7.5 is what we have. This is the sum of our squares divided by n minus 1 gives us 7.5, and so the last step is we take the square root of 7.5, and this gives us our standard deviation. So square root of 7.5, 2.74 is what I get. 2.74. And that is, this is our measure of spread. And if we had a different set of numbers, a different set of plant height growths, we would have a different standard deviation. But this is our standard deviation describing the different plant heights that we measured, 2.74. Okay. Are all the steps that I walked through here feeling okay? Yeah.
So that number is how far each of them are from the mean?
It's not. It's not how far each one is from the mean. This is a number that describes the spread. It can be thought of as the, quote, typical deviation, okay? The, quote, typical distance from the mean, but it's not exactly a measure of how far the numbers are from the mean. It's not even an average distance from the mean. It's maybe a typical number, okay? Just like when we find the mean or we find the median, it tells us where the center of the distribution is, but it doesn't mean that you actually have a number at that point or anything like that. It just kind of gives you an idea of where the center is. So another definition for the standard deviation, this 2.74, this can be thought of as the quote-unquote typical distance from the mean. Okay, so these are the 5 numbers that are recorded, and I got 2.74 as my standard deviation. Okay, let's say instead of 10, let's say the last number, the first 4 plants grew about the same, and let's say instead of 10, I had recorded 5 instead of 10. Okay, without doing any of the math, would the resulting standard deviation be larger than 2.74 or smaller than 2.74?
Smaller.
Smaller. Why?
Because 5 is closer to 10.
What's that?
Because 5 is closer to 10.
Because 5 is closer
No,
to
it's closer to
the
the number
center. Okay, we haven't even calculated the center, but 10 was, when we looked at the heights, we had 4, 6, 3, 7, and 10 was kind of a little bit larger than the rest of the numbers, okay? With, by changing that 10 to a 5, all of our numbers now go 4, 5, 6, 7, okay? Or 3, 4, 5, 6, 7, okay? And the numbers are a little bit more squished together, okay? If I did, instead of 5, if I had 0, okay? So one of the plants just didn't grow at all, okay? Would this number be larger or smaller than the standard deviation when we had the 5 in there?
Smaller.
It would be larger, okay? So, okay, so if we did 4, 6, 3, 7, 5, okay, let's say the standard deviation of 4, 6, 3, 7, and 5 ended up being, I don't know, 1.9. I'm just making up a number here, okay? Let's just say it was 1.9. If we plugged in 0 rather than 5, that resulting number of the standard deviation would be larger than 1.9. I don't know if it's going to be larger or smaller than 2.74. It's hard to tell, but it would be larger than this 1.9. Okay. Is that okay? Talking about the standard deviation.
But why would it be like you said,
Okay, because here now I've got numbers. So let's look at a number line. Okay, so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So right now, if I created like a histogram on this, okay, I would have a bar at 4, a bar at 6, a bar at 3, and a bar at 7. Okay, so actually these would be touching. All right, so if I put in 5, okay, so if we had 4, 6, 3, 7, and 5, I would have a bar right here, and you can see that the numbers are all kind of close to each other. Okay, but if instead of 5, I put in 10, okay, you can see that the numbers are now, they look like they're spread out a little bit more, okay? So that's why the standard deviation with 5 instead of 10 would be smaller, okay? Again, this is the pattern or the set of numbers when we have 5 in there. If I got rid of the 5 and I put in a 0, okay, you can see that it's now spread out again, okay? And actually it looks like it's just about as spread out as when we had the 10, so I think if we did the calculations with 4, 6, 3, 7, and 0, I'm pretty sure we would get 2.74, okay? If we did the calculations. All right, is that clear? What's happening there? I haven't done any math, but we're just talking about the standard deviation. Okay. So you'll have a few exercises in your homework asking about the standard deviation and things like that. Okay. So I'm going to take all of these steps to find the standard deviation and put it into a formula. And it might look a little bit crazy at first, but it's really, each of these steps, none of these individual steps is difficult in of itself, right? Or this is okay, right? Just let me know. All right, so the standard deviation, okay, and S is the abbreviation for standard deviation that we might see in the book. This is the formula for this. Okay, looks like this, okay? Square root of the sum of y minus y bar quantity squared over n minus 1. Alright, so in this formula are all 6 of these steps, okay? It's just not written out in a nice, neat way, but we'll decompose this formula, and I think it'll be clear that these two things are saying the same thing, okay? So first, first step 1 is finding the mean. That's given by this symbol. Y bar is the symbol for mean. Okay, and this is step 1. Finding the mean. Step 2 is this subtraction sign. That's where we subtract the mean. So we take each y and we subtract off y bar from each of them. That's step 2. Okay, so we do that for every number in our series, 4, 6, 3, 7, and 0, or 4, 6, 3, 7, and 10. Whatever numbers we have, we subtract the mean from each of those numbers. And that resulting number, we square. And we see that with that 2 right there. That's the third step. Square the deviations. The fourth step is to add up each of those squares. So take the squares and we add all of them up. That's the fourth one. Okay, the fifth one is to divide by n minus 1. And the sixth step is to take the square root. That's on the very outside. And that's step 6. So when you see a big complicated formula like this, a lot of times what you need to do is you start in the center or in the middle and you work your way out. So you start here at this y bar and you work your way out. You see that you subtract it off from each of the y's. You take this, you square the resulting values, you add all of them up, divide by n minus 1, and you take the square root of the final thing. Okay. Alright, so that's finding the standard deviation. You feeling okay? Alright.
So far.
Okay, so you will need to feel comfortable with being able to describe the spread. And ways to describe the spread, we've got the standard deviation, the range, and the IQR. You can use any or all, okay? Let's see. So yeah, when describing spread, okay, you can use the IQR, range, or standard deviation, okay? Or all of them, and or, okay? Commonly, the standard deviation is frequently used for symmetric distributions. But it's also used for skewed distributions. But probably the standard deviation is more commonly used for symmetric distributions. And the IQR and range, these are commonly for skewed distributions. But there's nothing wrong with using the IQR and range for symmetric ones either. Okay, so this is often what happens, and you just have to be comfortable with using all three. Okay, we have a question.
Yeah, it's about the formula. If y bar is finding the mean, what is y?
Y is each value
Of that
in your list. Okay, so when we were talking about the plants, we had 4, 6, 3, 7, and 10. Okay, each value, the 4 is a y, the 6 is a y, the 3 is a y, all 5 of these numbers is y, and you've got to subtract the mean from all 5 of those numbers. Okay. All right. So that wraps up chapter 4, and let me let's get into chapter 5. This they call comparing distributions, but really the big key here that we want to look at are making box plots, and then also and comparing distributions. Okay. So again, this is also for quantitative variables. Okay, so we're still working. So we're still working with quantitative variables. So when we're talking about distribution, we want to talk about how things are spread out, and we saw 2 tools that we could use to display a distribution. We've got the histogram and the stem and leaf plot. Okay? There's another graphic that we can use, and that's called a box plot, and it's an even more kind of compressed form of showing distribution. It's really you don't get a whole lot of fine detail. It's just a very just like the bare basics information is contained in a box plot. Okay, so histogram will give you a lot more information or detail, but it's also a lot, I guess, more challenging to make by hand. With a computer, you can generate these things quickly, but sometimes you want to look at a whole bunch of distributions all at once, and box plots allow you to do that kind of easily. Okay, so this is a very, I don't know, very much an overview picture. Data or distribution. So what a box plot looks like is you have a box. Okay, sometimes it's called a box and whisker plot, but you've got a box, and you have these lines called whiskers come off the box, and then sometimes you might see an outlier, either represented with a star or a circle. Okay. So this is what a box plot might look like. You can also see them rather than horizontally, they might be drawn vertically. And look something like that. Okay. And they look something like that. Okay. So the parts of the box. Okay. So let's look at the box first. There's 3 lines in the box. You've got the bottom edge, this middle line, and the upper edge. Okay, and in this box plot, we've got them down here, right here, and right there. Okay, there's 3 lines in the box, and that's going to be the first quartile, the median, and the third quartile. Okay. And we should all be comfortable finding Q1, the median, and Q3.
Point to the 3 lines again, sorry.
Okay, so I will we have Q1, the median, and Q3. On the vertical one, this is Q1. This is the median. This is Q3. Alright, so this is the box, okay? Alright, and this over here is known as a whisker. And we got two whiskers coming up, okay? So sometimes rather than box plot, they might call it a box and whisker diagram, okay? But before I can explain how to draw the whiskers, I have to talk about something called fences, okay? So we've defined the box, and although we don't see them on the box plot itself, there is something called a fence. There's an upper fence, and there's a lower fence, okay? Upper fence, lower fence. So we have three lines defining the box, and then we have two fences, okay? We don't include the fences in the final display, but we have to figure out the fences in order to draw the final display, okay? So the two fences, we have an upper fence, and a lower fence. Okay? And the idea behind the fences is that the fence defines what we call the quote normal range, okay? This is the zone of that we consider to be normal looking numbers or regular numbers, okay? Anything that's outside of this zone we consider to be unusual points, okay? So if we're talking about people's heights, all right, so I don't know, for men, the zone of normal might be something like what would it be? Maybe 5 feet to 6'6" or something like that. Okay, that might be the zone of normal. Okay, between 5 feet to 6'6". Okay, anybody outside of that zone would be considered I guess unusual or unique, okay? So if someone's taller than 6'6", like 6'8" or 6'10" or something, we would say, wow, that's really tall, okay? Or someone, if there's a man who's shorter than 5 feet, we would say, oh, that's pretty short, okay? In this range, the fences kind of define what we consider to be this zone of normal or typical heights or numbers or whatever we're talking about, okay? Not to say that something is really weird or unusual or anything like that when describing that, but this is what the fences help us define. Okay, so we've got, why did I push that up there? Okay, we have the upper fence and lower fence. So to find the upper fence, what we do is we take Q3 and we add 1.5 times the IQR. Okay, so we take Q3 and we add 1.5 times the IQR. So the IQR is what? Q3 minus Q1, and we take that and we multiply it by 1.5, and we go that far above Q3 to define our upper fence. Q1, the lower fence is going to be Q1 minus 1.5 times the IQR. That's how we find the lower fence. Okay. Now, if you read your book, there is a typo on page 90. Okay, page 90. There's a typo. All right. In the book, they have a plus here. Okay. Make sure that it's a minus. Okay, it's a minus sign. And so there's a typo there in finding the fences. Alright, so we have the two fences, the upper fence and the lower fence. And so the whiskers extend to the smallest number and largest number inside the fence. Okay, so we find the smallest number that's inside the fence and the largest number that's also inside the fence, and our whiskers extend to those 2 points. And then all other numbers, okay, so all the remaining numbers are outside of the fence. We indicate those with a star or circle. And they are called outliers. These are things that are unusually large or small. All right, so let's try a simple example. And so let's say I grew a whole bunch of these plants. I was really interested in how much a plant grows. Okay, this is now my new obsession, and I measure how much they grow after a week. And so we measure. This one goes. And because we've got it, so remember, when you're finding the median and the quartiles, what's the very first thing that you have to do with your list of numbers?
Put them in order.
Put them in order from smallest to largest. Okay. So just for time's sake, I'm going to go ahead and put them all in order from smallest to largest. So let's say I go 2, 2. Plants grew this much. Let's put okay, sorry. All right. Let's just say I grew 12 plants, and these were their heights. Okay. So a lot of plants grew 2 centimeters, 3, 4, 5, 6, or 7, and then I've got 2 plants that grew 15 and 18 centimeters. Okay. Oh, sorry. Let me. I hate doing this. Let me change one of these numbers to. Okay. Let's change one of those numbers. Okay. Sorry about that. Okay, so where is my median?
Between 5 right there.
5 and 5, right? So my median, what do? I do n plus 1 over 2th position number, so I do 12 plus 1 divided by 2. This gives me 6.5, so I find the number in between the 6th and 7th numbers. 1, 2, 3, 4, 5, 6 is 5, 7 is 5. So my median is going to be 5. Alright. What is Q1? Q1 is going to be in between the, so I look at this half list, and I have 6 numbers. And so Q1 is going to be the median of this half list. So this is Q1, and I get 2.5. Is that okay with everyone? Tell me if this is not okay. And then Q3, what do I have? 8. Okay, it's the number in between 7 and 9. I get Q3 is equal to 8. Alright, so let's draw a number line. time to do a good job of here. All right. So my box is Q1, the median, and Q3. So Q1 is at 2.5, so I draw a line at 2.5. My median is at 5, right there, and Q3 is at 8. Okay. So this is my box. 2.5, Q1, this is the median, 5, and Q3 is at 8. That's the box. Again, labeling. You don't have to label these on an actual thing, but for your sake, I am. All right, is this okay? Drawing the box. All right, once we have the box, we have to find our fences. So Q3 is 1.5 times the upper fence is Q3 plus 1.5 times the IQR. Okay, so what is my IQR? My IQR is 8 minus 2.5, 5.5. Okay, so my upper fence is going to be Q3 8 plus 1.5 times 5.5. Okay. So doing order of operations, you have to do the 1.5 times 5.5 first, and I get 8.25. So I have 8.25, and so 8 plus 8.25 gives me what? 16.25. Okay, so I'm going to draw an upper fence at 16.25. So 10, 11, 12, 13, 14, 15. So 16.25. I draw an upper fence right there. Okay, this is my upper fence. Okay, my lower fence, on the other hand, is Q1 minus 1.5 times the IQR. So I have 2.5 minus 1.5 times the IQR we established is 8.25. So I get a negative something, right? Negative 5.75. Okay, so I would have to count out, and I would have a lower fence somewhere down here. Lower fence at negative 5.75. This part okay so far? The upper fence and the lower fence. So once I find my fences, I draw whiskers to the smallest point and largest point that's contained inside the fence. So what is the smallest point that I have that's inside the fence? 2. Okay. So these are all of the numbers that I have. The smallest number that I have that's inside the fence is 2. So I draw a whisker that goes all the way down to 2. Okay, so it's not too far down from the rest. Okay. Yeah, the lower fence is at negative 5.75, but the smallest point that I actually have in my number of plant height growths is 2. And over here, what's the largest number that I have that's inside the fence?
18.
18 is actually
I'm
outside
sorry.
the fence.
I'm sorry.
Okay.
I was looking at
15. Okay, so 15 is the largest point that I have that's inside the fence. So I draw a whisker that extends to 15. Alright, so anything outside of the fence, so that takes care of everything between 2 to 15. 18 is outside of the fence, and so I draw a star or a circle out at 18. Okay, and that represents the outlier. So this tells us that we consider the plant height growths between 2 and 15 to be in our quote normal range, but 18 is an unusual point according to our box plot.
And there won't always be an outlier, right?
There's not always necessarily an outlier, right? If your largest point in your entire data set is within the fences, then there are no outliers. Okay. All right, making the box plot. Okay, yeah.
With box plots, and I know it's like graphically or whatever, how are you supposed to explain like the shape and stuff and like
Yeah,
spread?
so with the box plot, you can't really describe too much about whether it's unimodal or multimodal or things like that, okay? You might be able to look at the tails and decide if it's skewed or symmetric, okay? So looking at this, what does it look like?
Skewed right.
It's skewed right, okay? So you can see that we have more points above the middle, okay? Then we don't have more points above the middle. I'm sorry. We have an equal number of points above and below the middle, okay? But when we're talking about the points above the middle, they're more spread out and they go a lot further that way than they do this way. So it is skewed right. Okay. So looking at the tails, we can see that our box plot is skewed right. And yeah, so looking at this one would also be skewed right. This one would be symmetric. Okay. Yeah.
For like test purposes, what kind of questions do you answer with a box plot?
Yeah, so I'll probably have you guys create a box plot, or I'll ask you where's the upper or lower fences located and things like that. Okay. So given a data set, you should be able, given a set of numbers, you should be able to create a box plot on your own. Okay, and you will have a homework problem to make a box plot. Right. Okay, and so the box plot helps it. When we're talking about the box plot, we finally talked about the outliers. Okay, and these are points outside of the upper and lower fences. All right, and this is the final, when we're talking about the describing a distribution in CUS, this is the U in CUS. Okay. So if you find an outlier, it doesn't necessarily mean that this is a bad thing or anything like that. It's just something that was unusual, okay? Just like if you saw a man who was shorter than 5 feet, there's something in your brain that would say, oh, that's a little bit unusual. But there's nothing good or bad about that, okay? Sometimes in your data, okay, an extreme outlier could be a typo or something. Maybe somebody was typing in the data and they put the decimal in the wrong place, okay? You know, all of the transactions at the gas station are at least in the little store, probably under $10. But if somebody saw a $1,000 purchase at the convenience store at the gas station, and maybe they just forgot to put the decimal in there, okay? So you should investigate outliers, okay? So investigate outliers if you can. Okay. Never throw away an outlier just because, okay? Sometimes an outlier is inconvenient and throws off your results, okay? But you should never throw it away just because, okay? Do not throw away or ignore outliers just because. Okay, so investigate. If there is a justifiable reason to remove this point, then you can. But you shouldn't throw it away just because, okay? if you can't figure out what's happening or causing the outlier, you can do two analyses, one with the outliers included and one without. Okay, and you can say talk about how these outliers affect your analysis. Okay, but you shouldn't just throw them away just because they're. All right, so let's with box plots. Again, they kind of form a very much of a quick overview of what your data look like. And so let's just take a look at two box plots and let's see if we can make any descriptions comparing two distributions based on just the box plots alone. So let's have a comparing box plots. So these box plots we will draw vertically, and these are on roller coaster speeds. So this box plot represents the distribution of steel roller coasters, and this one represents the distribution of wooden roller coasters. Okay, so you go to Magic Mountain, and they've got steel roller coasters and wooden roller coasters and the like. Okay, and yeah, some are fast. So Superman the Ride, I think, is around 100 miles per hour, or so they claim. And that one would be a steel roller coaster. You've got Gold Rusher, which is like one of the slower ones. Okay, lame, someone says. Okay, maybe about 40 miles per hour. One of the earlier steel roller coasters, and then I don't know, they have Colossus and things like that. Those would be wooden roller coasters. And we looked at a whole bunch of roller coasters around the country, and these were our world, and this is what the distributions look like. Okay. So what can we say? What are some statements that we can say about the distribution of steel and wooden roller coasters? Actually, I drew this a little bit off. This line is right around here. All right, so comparing distributions. All right, so just overall, which set of roller coasters are faster than the other? Steel. Okay, and what makes us say that?
Larger spread.
Okay, so it's not the spread that we would be looking at. It is true. The spread of so that's one thing we can say is that steel roller coasters have a larger spread than wooden roller coasters in terms of speed. Okay, so when I'm talking about spread, steel roller coasters have larger spread than wooden. Okay, but just in terms of let's talk about the centers. What does it look like the median of steel and the median of wooden? So the median, this is the middle.
They're about the same.
This one's down here, okay? And the median of steel roller coasters is over here, okay? So it is higher. The median of the steel roller coasters is higher than wooden roller coasters, okay? So talking about center,